mathematicians. In this video, we see what is group action and we'll see some examples of group action and we see the what is orbit stabilizer theorem and its proof also. In the next video, I'll give some applications of orbit stabilizer theorem, which is a very important theorem in group theory. If you can understand, if you know some understanding of group action, then many problems related to group theory can be solved in a much simpler way. So that is why we want to learn group actions. Okay. Now, if you remember, a group is a set G together with a binary operation star. Okay. So if it is a binary operation star means it is a function from G cross G to G. Why we are considering the domain to be G cross G? Because we want to take two elements from the set G and we want to multiply it, we'll get a one element. Okay, so to multiply we need two elements. So we are taking elements from G cross G, so naturally we get two elements and the codomain is G, so the product will be a single element in G. Okay, so that's a binary operation, but binary operation satisfying more condition like closure property, associativity property, identity element and inverse. If it satisfies all this property, so if it is a binary operation, already it is going to G only, the codomain, so closure will be always there, only associativity, identity, inverse. If all this condition is satisfied, then we say G comma star is a group. In particular, in the group G, you can, if you take two elements from the set G, you can multiply. Okay. Now, when we come to group action, we what we want to do is you take a group G and a set X. Okay, and we want to define a multiplication between them. That means that you take a element of the group G and the element of the set X. Then we want to define some multiplication G dot X. In that is our aim, but we want that multiplication to satisfy some natural properties. For example, in case of group, we saw associativity, identity, inverse, that properties has to be satisfied. Likewise, in G, so like as I said, we want to multiply an element of G and an element of X. So we are looking at functions. I mean, our this operation star is from G cross X to X. Okay, so we want to multiply an element of the group G and an element of the set X, and the resulting multiplication element should be an X. Okay, so we're going to see a lot of examples of this and we will see why it is important also. Okay, so we say that a group G acting on a set X. Okay, that means that you have a function, say we call this function dot. Okay, so don't confuse with the group operation. So group operation we always denoted by star. Okay, so this is a group G, so it will have a binary operation that we denote by star. Okay, now this dot is a operation from G cross X to X. Okay, so given a element of the group G and a element of the set X, you can multiply them. The resulting element will be an element of X, and this multiplication should satisfy these two conditions. Okay, so if you multiply an element of X by identity element, you should get back the element here, and you take a X here. First you multiply by H here. Okay, so now H dot X will be an element in X. Okay, now on this element again you act by G, an element of the group G. So this is again an element of X. Okay, because this is an element of X and G is an element of G. So this will be again an element of X. This element should be equal to, first you multiply GH. Okay, so maybe as I said, we first do G star H. So in G, first you multiply these elements, you will get a one element of the group G and you multiply that element into X. Okay, so here first we are multiplying with X, but here first we are multiplying in the group G. These two elements should be same. Any multiplication satisfying these two conditions are said to be group actions. Okay, so again we'll see many more examples to understand this concept. Now you take an arbitrary element X belongs to X. What is orbit of X? Okay, orbit of X means, so you multiply all the elements of G, all the elements of the group G with this X, whatever element you get, they are called orbit. Okay, note that this is a subset of X. Okay, so if you multiply group element and if you multiply X, again you will get a element of X only. So orbit is a subset of X. Now stabilizer of X. What is stabilizer of X? So stabilizer means it is stabilizing X. Stabilizing means it is fixing. Okay. So if you multiply you look at all the elements of the group G, whichever when you multiply by X, you get back X. Okay. So that is a stabilizer. Basically, it is stabilizes X. It is not doing any changes to X. Okay, the group element into the set element will give you the element back itself. So G is not doing any changes to X. Okay, so such element if you collect in the group G, that is called a stabilizer of X. So stabilizer is a subset of G. One can prove that this stabilizer is a subgroup of G. So that is just a direct computation. So you take A, B belongs to stabilizer, then you can prove if A comma B belongs to stabilizer, then A B inverse also belongs to stabilizer. It is just one step verification. Okay, so I leave it to you guys to exercise. So this is orbit and stabilizer. So these orbit stabilizer two important concept in group theory, particularly in group action. Okay, so let's see some examples. So we'll take the group S3. Okay, S3 means symmetric group on three symbols 1, 2, 3. So it contains identity permutation. Then this was two cycle 1, 2, 1, 3, 2, 3. Then three cycles 1, 2, 3, 1, 3, 2. These are the six elements in S3. Now this S3 is my group. It is acting on this set 1, 2, 3. So this is my set X. Okay. Now I have to define a multiplication of a permutation and a number, right? So we have to define a multiplication of the group element and the set element. So I take a permutation sigma belongs to S3 arbitrary permutation, and I am going to define what is sigma dot 1, what is sigma dot 2, what is sigma dot 3. So basically here we are multiplying a group element with a set element. Okay, so sigma dot 1 I define to be the multiplication. Here only I am defining. So if I put this colon, it means that this is the definition. So we define the multiplication to be sigma dot 1 equal to sigma of 1. What is sigma of 1? Now sigma is a bijection. So you can calculate what is the image of 1. For example, if you take sigma equal to 1, 2, 3, this permutation, then 1 goes to 2, 2 goes to 3, 3 goes to 1. So sigma of 1 equal to 2, right? So we know how to calculate uh, sigma of 1, sigma of 2, sigma of 3. So note that these are all again elements of the set X. Okay. So if you multiply this permutation and this element of the set X, you again get an element of the set X. Okay. So this way we define a multiplication, yes, from S3 cross 1, 2, 3 to 1, 2, 3. Okay, we claim that this is a group action. So these two conditions you can directly verify. Okay, so it is very simple. So please check it once. Now we will calculate the orbit and stabilizers of various elements. Okay, note that orbit and stabilizer are defined for elements of X, not for G. Okay, so you take a X belongs to X and you can calculate orbit and stabilizer. So now I take 1. 1 belongs to the set X. What is its orbit? Okay. What is the definition of orbit? We quickly recollect. So you multiply this element of the set X by all the element of the group G. Whatever elements you will get, that is the orbit. Okay. So by this element 1 should be multiplied by all the element of the permutation group S3. Okay. So if you multiply sigma to the number 1, you get sigma of 1, right? So maybe I should write one more step that will be make better sense. So orbit of 1 is nothing but you have to multiply all the element of S3 to 1. Okay, that is the orbit. Now by definition sigma of dot 1 equal to sigma of 1. Okay, so basically you take all the permutations S3 and you look at the images sigma of 1 wherever 1 is mapped to under any permutation of S3, that is the orbit. Now if you notice, 1 is mapped to 2 by this permutation, therefore 2 belongs to the orbit. By identity permutation, 1 is mapped to 1, right? So if you take sigma to be identity, you get 1. So, and like if you take this 1 3, 1 is mapped to 3. Therefore, I mean the full set. This is equal to the full set is we are not that this orbit is a subset of x, so it cannot be something larger than x. Once orbit is equal to x, that should be the orbit. By so once you got all the elements of x in the orbit, that is the maximum. Okay, so we get orbit of 1 equal to 1 2 3. Similarly, for other elements also, you can conclude that the cardinality of orbit equal to 3. In other words, each orbit is equal to this set, the full set 1 2 3, on which the group is acting. So now we'll calculate the stabilizer of this element 1. So by definition, stabilizer is set of all element, maybe like stabilizer is set of all sigma belongs to S3 such that sigma dot 1 should be equal to 1. The sigma should not change 1. So that is the definition of stabilizer. Sigma dot 1 equal to 1 means sigma of 1 equal to 1 by the definition of the multiplication. Therefore, we want what are all the permutations that takes 1 to 1. Okay. So among all the 6 permutation, if you notice only this permutation, this takes 1 to 1, this takes 1 to 1. Okay. Therefore, stabilizer of 1 equal to these two elements. Okay, similarly you can calculate stabilizers of other elements also. So we have calculated stabilizer and orbit of all the elements. What we are observing is orbit of 1 has 3 elements, stabilizer of 1 has 2 elements. If you multiply the cardinality of stabilizer and cardinality of orbit for any element, you get cardinality of the group, that is equal to 6. Okay, note that this is 3 and this is 2. 3 into 2 6. Again, for all the stabilizer has order 2, all the orbit has order 3, and the product is 6. Okay, so similarly I have a couple of more examples. Okay, so you take so for a group action you need a G and a set X. Okay, if G is a group, then you can regard that as a set also. So you think G acting on G. This is possible. Instead of X, we take the group G itself. Okay, but already there is a multiplication in the group. That multiplication is star. But we can define some another using group action. We can define some another multiplications also. Let's see how to define it. So G acts on G. How? This is called a conjugation action. So you take a element G belongs to G and X belongs to G. I'm going to define their multiplication to be Gx G inverse, conjugation of X by G. Okay. Note that if you define group operation, like if you define this as a binary operation, it will not satisfy the required property to be a group. Okay, but this will satisfy, this multiplication satisfies all the property, that there are two properties of group action. These two properties will be satisfied. Okay, so that you can directly verify. So this multiplication will not give you group structure, but it will give you uh, group action structure. Okay, therefore there is a different multiplication, it is formed to, it is possible to define on G. Okay, that multiplication is on G is given by G dot x equal to Gx G inverse. Again we calculate the orbit of an element. So I take x belongs to this set G, this is my group G, this is my set G. Orbit of x equal to set of all G dot x such that G belongs to G. Okay, by definition G dot x, how the multiplication is defined? Group element, set element, the multiplication is Gx G inverse. So set of all Gx G inverse such that G belongs to G. This is precisely the conjugacy class of the element X. Okay, therefore under the conjugacy action, orbit of an element is nothing but the conjugacy classes of G. Okay, next we calculate the stabilizer. Stabilizer is set of all G belongs to G such that G dot x equal to X. G should not change X. But that is a stabilizing means. So by definition, G dot X equal to Gx G inverse equal to X. If you again, this means that Gx equal to Xg. Therefore, stabilizer of an element X is equal to set of all elements G that commutes with X. That is precisely normalizer of the element X. Okay, so normalizer is nothing but set of all elements in the group which commutes with the element X. Okay. So now again we see one example using the symmetry group for the same conjugacy action. So the group S3 acts on S3. Okay, recall that S3 contains these 6 elements. Now I fix this 2 cycle from the codomain. Okay, I want to calculate the orbit. Recall that orbit is nothing but the conjugacy classes. Conjugacy class of that element. In symmetric group, two elements are conjugate if and only if they have the same cycle decomposition. Therefore, orbit of x consists of, if x equal to 1, 2, then orbit of x consists of all the permutation which has a cycle type, this cycle type. What is the cycle type? This is a single two cycle. So whichever permutation is of the form single two cycle, they all belongs to this conjugacy class. There are only three permutations which are two cycles. So all of them will belongs to orbit of the permutation 1, 2. Now we want to calculate stabilizer of X. Stabilizer means that we just saw that for the conjugacy action, stabilizer is set of all permutations here whichever commute with this permutation. You can directly check that only these two permutation, identity and the permutation itself, are the only permutation that commutes with this permutation. Okay, therefore this is the stabilizer. Again, if you calculate the, if you multiply the r cardinality of the orbit and cardinality of the stabilizer, you get 6. This 6 is the cardinality of the group S3. Okay, so in like for x equal to 1, 2, we calculate x equal to 1 to 3. This element we calculate the orbit and stabilizer. So again, the orbit is nothing but conjugacy classes for the conjugacy action. Okay, note that for conjugacy action only the orbit is conjugacy class. Okay, for different action the orbit will be different. So two permutations are conjugate if they have the same cycle decomposition. Therefore, all the three cycles will belongs to the orbit because all the three cycle belongs to the conjugacy class of this element. Okay, so these two are the only elements which are belongs to the orbit of this element. Now, if you look at the stabilizer, stabilizer is set of all permutations commutes with this permutation. Again, you can see that these three permutations will commute with this permutation, and the remaining this permutation, this sorry, identity will commute with everything. These three permutation won't commute with this permutation. Okay, therefore, again we get R cardinality of orbit is 2, cardinality of stabilizer is 3, 2 into 3 we get 6. Okay, so we saw that in all the cases cardinality of stabilizer into cardinality of orbit of a particular element is equal to the order of G. This is what we observe, but that is true in general. That is what is called the orbit stabilizer theorem, very important theorem. I will give you many important applications of orbit stabilizer theorem in my next video. Also, there is a very important CSR problem asked regarding orbit stabilizer theorem. That is my next video. After that, I will give you other applications of orbit stabilizer theorem. Okay. Okay. So suppose G, we assume that G is a finite group, but in general, okay, yeah, we don't need a finiteness of the group, but so if the G is finite, then we can okay, I mean, doesn't matter. We assume the G is finite, and from the proof, you will understand why do we need finiteness. Okay, but you can talk about for arbitrary group, the statement is true. If it is a finite group, then you can the cardinality of G by stabilizer of X equal to cardinality of G by cardinality of stabilizer of X. This formula there, so G by stabilizer of X means set of all so, right cosets of the subgroup stabilizer of X. Okay, note that we proved that I gave you exercise. Stabilizer of any element X is a subgroup. Okay, so if it is a subgroup, you can count the number of right cosets of that subgroup. If you collect all the right coset of the subgroup, that set of all right coset is denoted by G by stabilizer of X. Okay, unless this stabilizer of X is a normal subgroup, this G by stabilizer of X is not going to be group. Okay, but whenever G is a group and H is a subgroup, this G by H just means that set of all right cosets of H. Okay, so the Arbit stabilizer theorem saying that number of right cosets or left cosets, number of right cosets of stabilizer of X is equal to the number of elements in the orbit. That is what it says. Okay. So in particular, if G is finite, then this cardinality of this number of right coset is given by cardinality of G by cardinality of stabilizer of X. Okay. Unless this number is finite, you cannot write this expression. Also note that this number is nothing but index of stabilizer of X in the group G. Okay, that is the index of a subgroup means number of right cosets. Okay, yeah. So let's prove this. So from this, if G is finite, then the left hand side you can put the cardinality of G by cardinality of stabilizer of X. So in particular, if G is finite, then cardinality of G equal to cardinality of orbit of X. This you can bring to the right hand side. You get cardinality of stabilizer of X. So you get order of G equal to order of orbit of X times order of stabilizer of X if G is finite. Otherwise, you get cardinality of orbit of X equal to number of distinct right cosets of the stabilizer. Okay, that is what we know for arbitrary group. Okay, so let's prove this orbit stabilizer theorem. So basically, we want to count the number of elements in the orbit. That is the idea. So by definition, orbit of X equal to Gx such that G belongs to G. Okay, here we make some observation. Note that here S3 acts on S3. So here the group G has 6 elements. The set X has again 6 elements. But here orbit is a proper subset of X. Okay, so it is possible that orbit is a proper subset. But if you remember in our first example, here orbit is actually equal to X because here S3 acts on this is my group G, this is my set X. So sometime orbit can be equal to the set X. Sometime orbit will be a proper subset. Okay. So we want to understand when two elements of orbit will be equal. Okay. So orbit of X equal to set of all Gx such that G belongs to G. So if all these elements are distinct, that is for G1 not equal to G2, if G1x not equal to G2x, suppose, okay, distinct elements of G gives distinct this product, then orbit of X will be equal to, in that case, you get orbit of, cardinality of orbit of X will be equal to cardinality of G. Okay, but that is not true. We just saw that orbit of X can be proper subset of X. It is possible. Okay, so that means that for two distinct elements of G, we might get G1x equal to G2x. Okay, so for distinct elements, you might get the same element. That is why the cardinality here is reducing. Okay, so in general, cardinality of orbit of X need not be equal to cardinality of G. It is possible that two distinct product can be equal for G1 not equal to G2. Therefore, here the cardinality reduces. If the cardinality is reduces, then you will have less number. Okay. So the question is when for distinct G1, G2, their images, I mean their product can be equal. That is the question. Okay. If for G1 not equal to G2, if you are getting G1x equal to, if you get G1x not equal to G2x, then clearly cardinality of orbit of X will be equal to cardinality of G. There is nothing to check. Okay, but what happens is for G1 not equal to G2, sometimes G1x can be equal to G2x. Therefore, it is not the cardinality of orbit of x is not equal to order of G always. Okay, it can be something different. So we want to understand when G1 of x equal to G2 of x. So G1x equal to G2x if and only if x equal to, so you pre-multiplied by G1 inverse in both the sides. Oh, sorry, G1 inverse both the sides. So you get x equal to G1 inverse of G2x. By the group action property, you get G1 star G1 inverse star G2 dot x. Basically, you can, this is like associativity. Okay, you can put it like this by the second condition of group action. So, x equal to G1 inverse G2x. That means that this element stabilizes x, because if you add, multiply this element with x, you get x itself. Therefore, G1 inverse G2 belongs to stabilizer of x. This implies that Hg1 equal to Hg2. So I take stabilizer to be H. Okay. Then I get the cosets corresponds to this G1 and G2 are equal, because HA equal to HB2, right cosets are equal if and only if A inverse B belongs to H. This we have seen from our basic group theory course. It is straightforward to, you can verify, it is verified. So the G A inverse B belongs to H means that HA equal to HB. Similarly, G1 inverse G2 belongs to stabilizer means the right cosets corresponds to G1 and G2 for the subgroup stabilizer, they are equal. Therefore, two elements in the orbits are equal if two right cosets of stabilizers are equal. Okay. Therefore, number of distinct elements in orbit of X equal to number of distinct right cosets of stabilizer. But number of distinct right cosets of stabilizer is equal to, that is, so number of distinct right cosets. That set is denoted by G by step of x. Okay. Therefore, cardinality of G by stabilizer of x equal to cardinality of orbit of x. Okay. So in particular, when G is finite, this cardinality is equal to cardinality of G by cardinality of step of x. Okay. So for in general, the index of the subgroup G in G is equal to cardinality of the orbit. Okay. So that is the final result. This is the orbit stabilization theorem that we want to prove. Okay. So this is the crucial application, crucial observation. Two elements in the orbit are equal if their corresponding right cosets are equal for the stabilizer. Therefore, this gives a relation between uh, orbit and the cosets of stabilizer. Okay, so try to understand what is happening. It is very important result. So I in my next video I will explain one CSA problem. We will solve that CSA problem using this idea group action, and in the subsequent video I will give you many interesting applications of this orbit stabilizer theorem. Okay. Okay guys, if you learned something new from this video, please click the like button and share with your friends, and subscribe my channel. If you want me to do some particular concept in mathematics, please like please use hash suggestion followed by, suppose, say Cauchy's theorem, like that. Please comment like this. I will do videos on that topic. Okay. Okay guys, thank you.